Hi there. In today's lecture, we are going to be looking at representations of complex numbers. So in the previous lecture, we looked at the so-called Cartesian form of complex numbers. So there we had the real axis and the imaginary axis, and we wrote z as the real part plus r times the imaginary part. So we had the following complex plane or Argand diagram with the real parts going along there, the imaginary part along there, and any complex number z we could write as x for the real part and r times y for the imaginary part there. Okay, so we could write it as z equals x plus ry. Now there's another way of writing that. Instead of using this Cartesian form, we could also use the polar form, because here's a point in a 2D plane. If we connect it to the origin, we get a radius, and this new radial line makes an angle with the real axis, makes an angle theta. So instead of using x and y, we can use r and theta, and that gives us the so-called polar form. So z is equal to x plus ry. We call this the Cartesian form, similar to the x and y that makes up Cartesian points. We can also write this as z is equal to x, we can write as r cos theta plus r times r sin theta. And this is polar form. Or it's also called the Euler form. Okay, and a nice compact way of writing this polar form or this Euler form is to write this as r e to the r theta. Now this looks quite strange and weird, but we'll see how this works shortly. Okay, and then this r, we can write it in a slightly different notation. R is the distance from the complex number to the origin, and in the previous lecture we said that this distance here we call the norm or the modulus of z, and we wrote it as absolute value sign z. Okay, remember that was the norm or the modulus of z. Okay, so that's, we can replace that for r, and e to the I, and instead of writing theta, this angle we sometimes call the argument of z. Okay, so that's just a bit of notation. The r and theta for the polar form we can write as the norm of z for that radial distance, and arg z or argument of z for the angle. Okay, but that's just notation. Now what's really weird is normally when we deal with exponentials, it's always e to the x, where x is a real number. Here we have e to the r theta, which is a complex number. So how do we handle the exponential of a complex number? So e to the x is fine. We know how to deal with that. E to the z, we don't know how to deal with that. So we don't know how to deal with e to the z. Okay, in the previous lecture we looked at adding complex numbers, subtracting complex numbers, multiplying complex numbers, and dividing complex numbers. We never looked at exponentiating complex numbers. How do we make sense of this? So this is our first look at what is called a complex function. It's a function like we had with real numbers, like e to the x, but instead of a real number x, we now have to deal with complex numbers z. Okay, so how do we deal with something like this? The way we deal with this is by looking at the Taylor series of the function. So e to the x, that gives us a Taylor series. k equals 0 to infinity, 1 over k factorial x to the k. And what we do in moving from this real number x to this complex number z is we just do a replacement. So e to the z is equal to the sum from k equals 0 to infinity, 1 over k factorial z to the k. And we know how to deal with this because z squared is just z times z. And we know how to deal with multiplication. Z cubed is just z times z times z. Okay. And we know from our previous work, repeated multiplication, that's fine to do. So this is how we deal with complex functions. So later on, we will look at some examples of complex functions. We won't directly use this Taylor series. We will have other tricks available. Okay, but you can always do something like this. You can take your real function, find the Taylor series, and instead of a real number x, you can put a complex number z, and that's how we deal with those functions. Okay, but in general, we won't be looking at that. Now, z, that's a complex number. What we want to show is that this e to the r theta is equal to cos theta plus r sine theta. Okay, because we factored out this r. Okay, and we're going to show that using this Taylor series definition. Okay, so we need to show, or need to prove, that e to the r theta is equal to cos theta plus r sine theta. Okay, so e to the r theta, complex function, we're going to use the Taylor series and show that that gives us cos theta plus r sine theta. Okay, so we start with the Taylor series. E to the z is equal to the sum from k equals 0 to infinity, 1 over k factorial z to the k. Now this is true for some complex number z. In our case, our complex number is I times theta. So e to the r theta is equal to the sum from k equals 0 to infinity, 1 over k factorial r theta to the k. Just a replacement there. Now r theta to the k we can separate into two parts. We can write this as e to the r theta is equal to the sum from k equals 0 to infinity, r to the k, that's a bit strange, but we'll look at this on the side, over k factorial theta to the k. Now, this looks similar to what we've seen before with these Taylor series, but this r to the k, that's new. R to the k is a complex number, but what kind of complex number is it? What's the real part? What's the imaginary part? Okay, we'll look at that on the side. So, r to the 0, that's going to be 1, right? 2 to the 0 is 1, 3 to the 0 is 1. The same thing happens with complex numbers. R to the 1 is just r. R squared, by definition, that's minus 1. Then r cubed, we can just multiply the previous result by I, and we get minus r. R to the 4, we can just multiply the previous result by I, and we get plus 1. And then r to the 5, we can multiply the previous result by I, and we get r. Okay, so that's enough terms to see a pattern here. Let's look at the even ones and the odd ones separately. So let's look at the even ones in pink. So r to the 0 is 1, r squared is minus 1. Then r to the 4 goes back to being 1. So we see this alternating behavior of 1, minus 1, 1, and the next term will be minus 1. Let's look at the odd ones. So r to the 1 is I to the 3 is minus r to the 5 is I again. So I, minus I. They also alternate they don't alternate between 1 and minus 1, they alternate between I and minus I. So let's make a note of that. The even terms alternate between 1 and minus 1. So the even terms alternate plus or minus 1. The odd terms alternate plus or minus I. Okay, so we have this separation of terms into the even ones and the odd ones, which means our Taylor series here will also be split into an even part and an odd part, depending on the value of k. So e to the r theta is equal to the sum from k equals 0 to infinity. Let's look at the even terms. They alternate between plus or minus 1, so we can write minus 1 to the k over 2k factorial, because it must be even, not x, theta to the 2k, plus, and then for all the odd terms, we have this common factor of r, so we can take that out the sum. And then we have the sum from k equals 0 to infinity. These also alternate, minus 1 plus 1 minus 1 plus 1, all times by r, divided by 2k plus 1 factorial, because those are the odd ones, theta to the 2k plus 1. Now, if we look at the first term, we've seen that before. That's the Taylor series for cos. And the second term, that's the Taylor series for sine, multiplied by r. So e to the r theta is equal to cos theta plus r sine theta. Okay, and we call this Euler's formula. Yeah, and this goes back to that Euler form that we had at the very beginning. So z is equal to r cos theta plus I r sine theta. We can write that compactly as r e to the r theta, because we've now proven that e to the r theta is equal to cos theta plus r sine theta. Okay, so now it's a compact way of writing these complex numbers, and we'll see that that will be quite useful in our later work. Okay, let's have a look at some examples. Okay, so we have z is equal to 1 minus r. This is written in Cartesian form, x plus ry. We would like to write this in polar form as r e to the r theta. So the first thing we need to find is the modulus of z, or the norm of z. That's going to be root of 1 squared plus minus 1 squared. That's going to be root 2. And what about the angle? So theta, remember back to when we did polar coordinates, this angle theta we can write as arctan of y over x, so it's minus 1 over 1. So that's going to be arctan of minus 1. That's going to be minus pi over 4. So putting this together, we see that z is equal to the modulus of z, which is root 2, e to the minus r pi over 4. And we can represent this with a little diagram. So we've got the real part, we've got the imaginary part, and here the radial distance is root 2, and the angle is minus pi over 4, so that's going to be somewhere here. So here, minus pi over 4. So positive angles, they go counterclockwise. Negative angles, they go clockwise. And this distance is root 2. And this makes sense, because if we look at the original number, 1 minus I means 1 along the real line, minus I means we go down, and that's exactly what we've got there. Okay, so that's just a quick check to see if that's right. Let's look at another example. Okay, so here we have z is equal to 1 plus I root 3. Again, this is in Cartesian form. We've got the real part and the imaginary part, or x plus iy. Okay, let's find the modulus of z. That's going to be root 1 plus 3, that's root 4, which is 2. And the theta, or the argument, that's tan inverse of y over x, so that's root 3 over 1. That will be pi over 3. Okay, now that we've got these two parts, we can write z as modulus of z, which is 2, e to the r theta, so that's e to the pi over 3. Okay, so that is the polar form for this complex number. And we can write a little diagram here. We've got the real part, imaginary part. The radial distance is 2. We've got a positive angle pi over 3. So that's going to be somewhere like here. So that's pi over 3, distance 2. And that's our z over there. Which makes sense. If we look at this here, we've got 1 along the real axis, root 3 along the imaginary axis. This looks about right. Okay, so positive real, positive imaginary, so it should be somewhere there. Okay, so if you're unsure about this angle, to see if you got it right or not, just draw a quick diagram, and you can see, is the real part positive and the imaginary part positive? You should be here. If the real part is negative and the imaginary part is positive, you should be up here. If the real part is negative and the imaginary part is negative, you should be down here. And if the real part is positive and the imaginary part is negative, you should be down here. Okay, so that will give you an idea of which quadrant you should be in. Okay, based on the angle. So 0 to pi over 2, quadrant 1, pi over 2 to pi, quadrant 2, and similarly for 3 and 4. Okay, so that's how you can go from angles to Cartesian or Cartesian to polar. Okay, by looking at the angle here. Okay, so that will be it for today's lecture. There won't be any homework for this. So the only homework that is due for the Thursday is from the previous lecture. Okay, reminder that that homework is due before the assignment. Okay, so the assignment will take up the whole tutorial period, so you won't have time to do the homework during that period. Okay, it will be due before we start with the tutorial. You may submit your homework before then, that's perfectly fine. I will be in my office on Wednesday and for most of Thursday. Okay, so remember that the assignment is Thursday afternoon, so you can submit the homework before then. Okay, and if you have any questions about the homework, again, you can email me or you can come to my office. Okay, so please remember, like I said in the previous lecture, I won't be available on the Tuesday. You can still email me, but I won't be in my office for Tuesday. Okay, I will be there Wednesday and Thursday if you have any questions. Okay, and remember for the assignment, the scope is everything that we've done this semester so far. So that's up to and including the Taylor series, okay, which we looked at before the semester break. Okay, as always, if you have any questions, please email me or make use of the tutors. So you should all be on the WhatsApp groups with them. Please just let them know if you have any questions. Okay, they're there to help you out. Okay, so I will see you on Wednesday if you come to my office, or on Thursday for the assignment.